let me start first talking about acids and bases. And so water is formed and can break down into two different ions, a hydrogen ion and an OH with a negative charge, and that's called a hydroxide ion. And a hydrogen ion is a classic example of what an acid is, and the hydroxide ion is a classic example of what a base is. And so acids are going to be molecules that can release hydrogen ions, and bases are those that can accept hydrogen ions out of the solution. So acids can release a hydrogen ion into the solution, and then it can bond to a base, usually by combining the hydrogen ion to a hydroxyl ion to form water is a common way. Okay? And the word alkaline is a synonym for the word basic. So we can talk about chemicals being acidic or basic. That's really a thing more for chemistry. For us, we're going to be talking about acids and bases in generalities and how they relate to the pH scale. So pH stands for potential hydrogen. So in other words, how many hydrogen ions are there that are positively charged? And so if we have lots and lots and lots and lots and lots of hydrogen ions, then we have what's called a low pH. Notice these are opposite of each other. High hydrogen is low pH. And conversely, if we have low amounts of hydrogen ions, that means we're going to have lots of those hydroxyl ions. Okay, so low hydrogen ion is going to be high pH, is going to be high hydroxyl. Okay, and remember the hydroxyl, those are bases. And so our pH scale goes between 0 and 14, with 7 being considered neutral. Okay, does not mean 7 in your body is neutral. Absolutely not. Most people with a body's blood pH of 7 are dead. Okay, so we will talk about that later. But when we're talking about water, acid rain is rain that has a pH lower than 7. Which is pretty much rain anywhere close to an industrialized city. Okay, so substances with pHs of lower than 7 are considered acids. Okay, and so vinegar, lemon juice, battery acid, your gastric pH. Okay. So those things have really low pHs, which means they have really high hydrogen ion concentrations. And then those items that are alkaline or basic have really high hydroxyl concentrations and really low hydrogen ion concentrations. And so baking soda, milk of magnesia, you buy over the counter, the ammonia you use for cleaning, or the lye. And so just remember two things about this pH scale. First thing, water, we're talking about a pH of 7. The water for our lab experiments has been brought back to a neutral pH of 7. The second thing is the inverse relationship between hydrogen ion concentration and pH. As hydrogen ion concentration goes up, pH concentration goes down at the same proportion, but not exactly, because it's not that we are doubling from a pH or we're having from a pH of 1 to a pH of 2. Each of these is a 10-fold change, just kind of like the Richter scale when it comes to earthquakes here in California. It's a 10-fold change going on, or it's logarithmic scale as opposed to a normal linear scale. Right. Now, what our body does to try to prevent changes in pH is we have buffers. And what a buffer is a molecule that helps prevent the pH change. Like, for instance, we can have buffers which will absorb hydrogen ions if an acid is added, or they can absorb hydroxyl ions if a base is added. Okay. And so if we don't have a buffer in the solution, for instance, in this solution, which is started with a pH of 7, if we add acid to it, you can see the pH has fallen to 4. But if we put it in a solution that contains a buffer, then we can see the pH only dropped to 6.9. So it didn't 100% change it, but it prevented the vast majority of changing. And in the same example, if we add the hydroxyl base to it, we can see here that the pH went from 7 to 10.5. But in the appropriate buffer for hydroxyl ion, you can see the pH only went to 7.1. And so this is critical for us to maintain homeostasis, to have these buffer systems. And in our human bodies, we have 3 main systems. One has to do with carbonic acid, which is an equation, which hopefully you know, carbon dioxide and water forming carbonic acid, which then spontaneously dissociates into a bicarbonate ion and to a hydrogen ion. Our proteins are also buffers, and then we also have a phosphate buffer system. And we have different buffer systems for different roles. Like for instance, in our blood, our biggie is going to be a bicarbonate buffer system. And yes, the other ones are there, but they have minor roles. Extracellular fluid, once again, is bicarbonate, but phosphate intercellular things are important as well. Inside the cell, it's not a bicarbonate system at all. It's the proteins and the phosphate systems which take over. And in our urine, it's different systems whatsoever. We still have the phosphate system, but then we also have ammonia and ammonium acting as buffers as well. So when we get to the right parts of the body systems, we will learn about the specific buffer system and how it works to keep us in homeostasis. All right, so here's some questions for you to go ahead and answer. So stop it. They're very simple. They're not complicated at all. Just go through the answers and then see if you can answer them correctly. And now I'm going to move on to water mixtures, what a mixture are. And the mixtures, we have names for 3 different types of mixtures, and it has to do basically mostly with what is the size of the particle that we are mixing with the water. Okay, and then because of that particle size, something happens to light rays, and you can do this little experiment at home using, you know, the little flashlight on your cell phone if you want. So the first thing is a solution, and this is the word you hear a lot in chemistry, and these are when we're using really small particles, and what happens is the particles are evenly dissolved throughout the solution. It's very homogeneous. There's no settling of particles, and when you put a light through it, it goes right through it. There's no scattering of the light. Now, if we look at the ones with the largest particles, they are going to settle out very quickly. The liquid's going to look very cloudy, or you won't be able to see it at all. And we will have, this is an example of this is if you mix flour with water. It's like you're making a dough. Okay, before it forms a dough, you don't have enough flour for that, but you're just going to have this cloudy liquid that we're going to call a suspension. Okay, if you put the flour in the cup and you have the cloudy liquid and then you let it sit there overnight because you're too tired to do your dishes in the morning, you will see a white layer on the bottom where all the flour has fallen out of suspension and has precipitated at the bottom of the liquid. And in between the tiny particle size and the big particle size is the mama bear colloid, where we're going to get a milky appearance. Positive example, something looks like milk, it's a colloid. Okay. And what's interesting about some colloids, some will contain proteins that are liquid when they're warm, but then they will gel when they cool. And this is an example of this are the agars we use for microbiology to play your organisms and grow your organisms in micro. So you'll have lots of experience with agar. And you also see this if you watch cooking shows and they're using agar so they can make little balls of whatever it is that they want to put in the food. They're creating colloids. So once again, here's another slide with 6 pictures for you to figure out which type of mixtures are being represented by the 6 different pictures. And With that, I am done with this section. So thank you again for all your hard work. And I will see you as we do the last section of the chemistry of life, which has to do with macromolecules.